Number 14, a 5 kilogram block with speed of 8.1 meter per second travels 2 meters along a horizontal surface where it makes a head-on perfectly elastic collision with a 15 kilogram block which is at rest. The coefficient of kinetic friction between both blocks and the surface is 0.35. How far does the 15 kilogram block travel before coming to rest? Alright, so there are lots of information to begin with. I'm gonna first draw our system. So here's our horizontal surface, and here's our initial block, the smaller mass that's moving 8 meters per second. And this is 5.0 kilogram. And then 2 meters away we have a bigger block, stationary, not moving. So V initial is 0 meter per second. And there is a force of friction acting against our motion of our block. And ultimately we want to know the distance our big block stops after the collision with the smaller block. So the final of our big block is gonna be 0 meter per second. Alright, so we would like to know this distance. So I'm going to set that equal to x. Our goal is to find the distance of x. And we expect this to be meter. And we are given this distance is 2 meters. So let me tell you the strategy I'm going to use. So the first frame of reference will be this side. I'm ultimately interested in the speed of this smaller block right before the collision. And at the collision, you have momentum, conservation of momentum equation, and also the conservation of energy equation. So you have two of them. 2 and 3 will involve with the collision strictly. And then finally, the fourth frame of calculation will only deal with our big block exclusively, and the only force that's resisting our motion to help it stop is the non-conservative force, the frictional force. Therefore, I'm going to start with our step 1. Find the speed or velocity of smaller block just before it collides with the stationary big block. Alright, so let's write down the necessary information. For the first step, we have an initial velocity, 8.0 meter per second, and the mass is 5.0 kilogram. The distance is 2 meters. Okay? And we're gonna set up the equation that deals strictly with our smaller block. So 1/2, before I say that, I'm gonna start with the kinetic energy initial equal kinetic energy final plus the absolute value of the non-conservative energy, which arises from the friction along the ground. So initial kinetic initial is 1/2 mv 1 okay, I squared, and 1/2 mv final squared plus the mu, the coefficient of friction, mg, which is our normal force, and the cosine 180, but we made the absolute value around, so we don't have to worry about that. And that's it. Oh, don't forget the distance. Now I can multiply 2 on both sides and then cancel out the mass present. And I'm very interested in this part, the final velocity of our smaller block just before it collides. So let's refine our equation. So on the left side I have vi squared equal v final squared plus, don't forget to multiply by 2 on our third term in this equation, so 2 mu gd. Okay, now I can move the 2 mu gd onto the left side, so v squared minus 2 mu gd equals v final squared. And now I can just plug it in. The initial velocity was 8 meters per second, so that becomes 8.0 squared minus 2 mu 0.35. Okay, I forgot to write down this part. Okay, so 2 times 0.35 times 10 gravity constant times the distance is 2.0. Well, I need to square root both sides to find the velocity final. You're supposed to get 7.07 meter per second. Okay. Now we just finished the first part. Now we're gonna move on to the second and third part. So the second and third part exclusively deals with the collision of our system. So step 2. Use conservation of momentum. By definition, it is mass times the velocity plus mass, the bigger mass, times the velocity of our second block equal mass times the velocity of our first final block, final speed of our first block, plus mass times, so you get like this equation. We're given that the initial velocity of the big block was 0 because that's stationary, so we can just cancel that out. And also the final velocity we found from the step 1 now becomes the initial in our second frame of our reference here. Okay, so v initial now becomes (7.07 meters per second) for the first block. So we can plug this value in here. Alright, so now I'm gonna plug it in. We're really looking for this, but you will notice that this one equation will not be sufficient. But for now, I'm just gonna perform the calculation. So smaller block was 5 kilograms, you saw up there, so 5.0 and then 7.07 equal, that's 0, 5.0. We do not know the initial velocity, I'm sorry, the final velocity of our first smaller block, and also we do not know the final velocity of a big block. But we really want to know this guy, so I'm going to write that in red font. You will notice that we can divide both sides by 5. And that simplifies to 7.07 equal V1F plus 3 V2F. I'm going to set that to be our equation 1. Now for our step 3, use conservation of energy. So we have 1/2 mv squared just like earlier. We can cancel out so what is this? Oh, let me read it first. We can cancel out this part because we know the initial velocity of our big block was 0. Okay, that goes 0. So just like the step 2, we're gonna have everything except the final velocity of the small block and the final velocity of the big block. Plug it in. 1/2. Mass is 5.0. Velocity. So that's also coming here. (7.07) squared equals 1/2 5.0 times velocity final of a smaller block plus 1/2 m. Oh, that's 15. Notice we can also multiply by 2 and divide by 5. On the left side I have 50. On the when you multiply 2, divide by 5, you have a velocity final for the smaller block squared, and this is what you get. I'm gonna set that equation 2. So I have to combine both equations. So my strategy is to keep the V2F here. So I'm gonna set V1F equal 7.07 minus 3V2F. I'm going to displace this. On here. So I have 50 equal 7.07 minus 3V2 final, and then you square that, plus 3 times this. So when you square this, you're gonna get 50 minus okay, you're gonna get 42.42 V2 final plus 9 V2 final plus 3 V2 final. So these are the like terms. You get 12 V2 final squared, and you can divide by the V2 final, and 42.42 divided by 12, you get 5.35 meter per second. .535 meter per second. Okay, strategy is just divide by the same. You do know that zero doesn't count. You can have zero on our calculation, so you can ignore it. So, and then you just have to divide by 12 on both sides, and you get 3.535 meter per second. So we are only done up to part 3. Now let's go back to our equation. It's a long problem. Now we have to tackle this one to finish our question. This one. So we just finished the first, second, and third, and we'll use the fourth to finish our journey here. So step 4. Step 4 is just find x using conservation of energy. Now we can ignore the smaller block. It's independent from our force frame. So conservation of energy. So we have kinetic energy that it gained from collision of our big block, and we have kinetic energy final, but that's going to be 0 because we have non-conservative energy acting against our motion. Okay, you can have NC if you want. Some textbook has that. I just like friction because that's more specific. One thing you have to be careful is that final, that really means final. This is the friction. Actually, you know what? I will just use NC just in case students get confused on that. So let me also correct maybe that part as well. So instead of F here, I'll write the non-conservative energy so that you don't get confused with the final. Okay, so coming back to our focus here. So that final velocity in the frame 2 and 3 actually becomes initial velocity. Okay, it's a big block, so I'm gonna be more specific. But we don't have to worry about V1, V2 because, like again, I said, concerned with only big block. One half. You know, you don't have to write anything for our final because it's stationary, or we are looking for when the big block stops, so that just takes 0, and the non-conservative becomes the mu times the normal force, and big N, G, and X is what I initially chose. So we have to find the distance. So mass cancel out. Just plug it in our initial velocity. And then divide by our mu and G. Mu is 0.35, G is 10, 1/2 times, and 3.535 squared. You get you get 1.785 meter, and you can approximate to 1.79 meter, and that's our final answer. And let's check if we have it. And we do. 1.79. It's a long problem, but still got the right answer.